Hi, my name is Mikhail Mishin. Today I will present my thesis topic, which is anomaly detection algorithms and techniques for network intrusion detection systems. The project was carried out at Ericsson, Finland in collaboration with Aalto University. Okay, so first let's look at the table of contents and of the report, and this presentation will loosely follow the structure. We begin with the introduction, where we give the context of the problem and motivation. Furthermore, we define the research questions and methods. Then we provide an overview of the related works. Next, we give a background on two related fields to the topic of this thesis, which are networking and anomaly detection. Then we discuss in more detail what is network intrusion detection and how can we apply anomaly detection techniques in this domain. Then we present the datasets that we used in this work for our experiments, and we conduct some data analysis and identify the properties of the datasets. In the section 6 experiments, we define the experimental methodology, present the obtained results, and discuss the findings. And finally, in the section 7 conclusions, we draw conclusions, make conclusions that give answer to the research questions stated back in section 1, and we identify the directions of future research and limitations of the study. Okay, so let's begin with talking about what is a network intrusion detection system. And basically, the system is used to protect a computer network against malicious activities, which we call cyber attacks. And the way it works, it collects and stores network traffic, and then it applies some techniques to analyze the traffic data and find possible traces of attacks. And examples of attacks include port scans, denial of service attacks, device infiltration, and such. And in particular, we focus on anomaly-based needs. And the difference is that they use an anomaly detection algorithm to detect attacks. And the key assumption here is that we use this anomaly detection algorithm to model the normal behavior, normal traffic. And then we assume that attack traffic is somehow deviates from the normal traffic, and our model, anomaly detection model, will detect it. Okay. So next, let's actually look at the research questions now that we understand the concept a little better. So we target basically three research questions, and the first is we conduct a comparison, empirical comparison of the algorithms, anomaly detection algorithms, focusing on deep autoencoder based models, and we compare them with the two models based on classical approaches. Then we look at this concept of aggregating, computing aggregated statistics of network traffic, and we'll define this a little bit later in this presentation. And we want to know if it improves the general overall performance. And next, the third question is what kind of attacks can be efficiently detected using this the combination of the above techniques. So now let's see how we answer these questions. Well, first we define our experimental methodology, which is we select the algorithms and data processing techniques and training and evaluation procedures. We conduct the evaluation on three public network intrusion detection datasets. So we use three in this case to kind of arrive at more general results, to not overfit on a particular dataset. Concretely, we use this CTU13 dataset, CICIDS 2017, and IoT 23, and again, we'll briefly go through them later in this presentation, so I'll leave it out for now. And after we have selected the data, we conduct some data analysis to understand the data better, and then we carry out the experiments and analyze the results and report. Right. So now let's move to more to the background. As I mentioned, we are focusing on anomaly-based network intrusion detection. So let's first talk about what is anomaly detection in general. And it is a machine learning task that to find observational patterns in data that have somehow uncharacteristic behavior, so different from normal, deviate from normal. Here we should say that there are different kinds of anomalies, such as point anomalies, contextual, collective, and this is explained in more detail in the report. Different learning modes of the algorithm. This is actually the same with the classical machine learning tasks, so we can have supervised, semi-supervised, and unsupervised operational mode. Anomaly detection models typically assign an anomaly score to each input instance, and anomaly score is a measure of the degree to which that instance is considered an anomaly. And here we follow the convention, the higher of anomaly score, the better. So we can define a threshold above, if you want to classify each instance as anomalous or not, the easiest way is to define a threshold and say that all the instances that have anomaly score higher than the thresholds are anomalies. So what anomaly detection algorithms do we consider? As we mentioned, we focus in this work on deep learning autoencoder based models, including the basic variation, just an autoencoder, and then two more advanced probabilistic versions, a variational-autoencoder and an autoencoding Gaussian mixture model. And the key assumption we make here is that autoencoding models that utilize deep neural network are able to model complex data such as network traffic better than algorithms based on classical paradigms. And here we consider two other algorithms, such algorithms, isolation forest, which is a tree-based anomaly detection algorithm, and Mahalanobis distance. And let's just briefly describe how we can use basic autoencoder for anomaly detection. So the general concept is that an autoencoder learns two functions, like an encoding function and decoding function, and for original input, and it uses the encoder to obtain a compressed representation, and then it uses the decoder to reconstruct the input with some loss from their compressed representation. So how can we use it for anomaly detection? Well, we train it only on normal data. And since this model is data specific, then anomalous data points that somehow are different from normal data points will have high reconstruction error if the training procedure was done correctly, and then we will be able to separate them from the normal data points based on the reconstruction error. So again, normal points have low reconstruction error, and anomalous data points have high reconstruction error. Alright, so let's move on. Now let's talk about how do we store network traffic and what are our data points here. So a common format to store network traffic is so-called network flow format. And here you can see like an example of this log. And basically network flows define connections between network computers, like individual connections. So they are identified by source IPs and ports, and destination IPs and ports, and protocol. And then they can have such attributes of a connection, such as flow duration, number of packets transferred, amount of bytes transferred, and many other statistics can be added here. It depends on the network flow exporter that outputs these logs. And we call this, so a data point here is a network flow, and in this work we call it a no-agger, because there is no aggregation, which we will talk about on the next slide. So now network flow aggregation, and this was the kind of related to the second research question that was stated. So what is this operation? We basically group network flows by unique source IP address and calculate new descriptive statistics during some aggregation window. So we transform our data points to be now the network statistics of a single source IP address within like an X minute period. And for example, we can calculate the number of flows that this device had, this IP address had, and the number of unique destination IP addresses, and like the maximum flow duration during this period. And the intuition behind this is that we are looking at the problem from like a different perspective, and this operation of aggregation can reveal new patterns that will help for the detection. And in this work, we experiment with two aggregation windows, concretely 1 minute aggregation window and a 3 minute aggregation window, and we denote them as Agg1M and Agg3M. In comparison, on the previous slide, we talked about just network flows being the data points, and those data points we denote as no Agg. And maybe one point to note here, aggregation further helps us by reducing the number of data points, which is really large in case of computer networks. So this is helpful, just easier to work with. Let's now look at the datasets, and I will be brief here. So the first dataset is CTU13. It is has captured traffic from a university network, and the authors executed 13 botnet attacks presented in this table below. We won't go into detail in the table, but you can see that such attacks as DDoS and different web scans and command and control communication were executed. So 13 different botnet attacks. And here's a like visualization of the first attack. And on the left we see like the network flow data points, so without aggregation, and blue are benign data points, and orange in this plot are attack data points. And on the right we see, and this basically shows you the rate from the start of the like from this attack. And on the right we see the picture after aggregating, computing aggregated statistics over the window of 3 minutes. And we kind of can see the picture is different, and if we look at the percentage of the attack data points, that also changed from 1.45 to 0.01. Right, so the second data set is CICIDS 2017. The network traffic was emulated using special software, and also contains a wide range of executed attacks, including DDoS, port scans, botnets, and so on. Again, the attack scenario, an example, and we can see how the picture changes when we do the aggregation. In this case, pretty significantly, since it's a DDoS attack, and there were a lot of network flows in the first, on the left picture. Attack flows, that is. Next, we look at IoT23. This dataset contains captures from IoT devices, and various botnet malware was executed on the devices, and that also performed various malicious actions, such as horizontal port scans and file downloads and DDoS attacks. And again, an example of the attack scenario from here. Okay, so let's move on to our experiment setup. So we choose to train and evaluate the models in the semi-supervised mode, and concretely this means that in our train batch we have only orally normal data points, so no anomalies. And then we select an anomaly detection threshold and hyperparameters on so-called threshold batch, which contains both normal and anomalous data. And then we evaluate the model on on a batch of unseen during training normal and anomalous data points, which we call the test batch. And our main performance measure is the F1 score, since we have like class imbalance here. And so as we mentioned, we experiment with both network flow data points and aggregated statistics. And lastly, we consider two ways of splitting the data, the original data, into train, threshold, and test batches. The first scenario is that we split data points at random, and in the second scenario we split by different attack types. So we say that some attack scenarios are only used for training, and then we hold out the others for testing. So in this second scenario, the testing attacks were completely unseen during training. So in a way, we're testing for evaluating how well the model will detect a novel unknown attack. And just a few words how we select the threshold and the hyperparameter. So we have this threshold batch which contains a mix of normal and anomalous data points, and we basically select the threshold that maximizes the F1 score. And you can see on the precision recall curve we want to get to this upper right corner where precision and recall are both 100%. Okay, so let's jump to the results. Here you can see the precision recall curves obtains for all three data sets and for non-aggregated data points and aggregated data points. And from this table here we can see that the precision recall curves look better for the aggregated data points because they get closer to that upper right corner. So we can already see that this aggregation seems to improve the performance in general, overall. So on this slide, we can the main research question of this thesis was to conduct an algorithm comparison, and so we used this statistical test to make this critical diagram. We use a statistical testing for make this critical diagram, and briefly we rank the algorithms from 1 to 5, 1 being the best performing algorithm. And then based on the performance, like averaged over all benchmarks, we put them onto the scale, and with the bold lines we connect the algorithms that are like statistically close to each other in a way. So we can't. There's not enough evidence to say that they're that they perform. That some perform better than the others. However, from these diagrams we can see, and we do it both for split at random benchmarks and split by scenario benchmarks, which I described a little bit earlier. And from both of these diagrams we can see, for example, that autoencoder and variational-autoencoders seem to outperform the other models. And furthermore, we can say that the statistical difference is significant for if you compare it to Mahalanobis distance and autoencoding Gaussian mixture model, for example. And let's just look at some successful and unsuccessful examples. So here's a successful detection example from the IoT23 dataset, and this is a variational-autoencoder trained on aggregated data points. And we can see that it managed to almost completely separate the attack and benign data points in this for this attack for this test attack. Benign data points are denoted as blue in this plot. So yeah, again we can see clear separation, so it does a good job. But then this is in fact the very same model for another test attack, and you can see that although it does somewhat separate the attack and benign data points, again benign are blue, but the selected threshold is inadequate for this scenario, and we miss a lot of this command and control communication. For example, most of it kind of gets undetected, so there's a chance that we miss this attack. Yes, so in general we observed that some attacks, the models would succeed at detecting a few attacks, and then they would kind of fail at detecting some others. So there's a lot of variance in this. Although the overall performance might be good, some particular attacks may be missed. But here let's jump to the conclusions and basically let's give the answers to the stated research questions. And the first answer, as we saw on the critical diagrams, that variational-autoencoder and autoencoder seem to be the most robust and best performing models compared to the other algorithms. And as we saw on the precision recall curves, and furthermore in the report there are more supporting numbers, network for aggregation generally improves the performance and seems to be like a good thing to do. As for the third research question, we identified, although this was not presented in detail in this presentation, but we identified that majority of the attacks that contained in the datasets that we experiment with have good or moderate detectability, so we are able to detect them using some models. But that said, we have observed a lot of variance kind of among the best performing models, so no model succeeded at detecting like every attack. They always were good at detecting a few, and then were a little bit worse at detecting some others. And we hypothesized that there are maybe two ways to explain it. The first is that the different attack types like exhibit different characteristics that make them suitable for application of a particular method, or that the models just get lucky somehow during the optimization. Lastly, let's look at some identified challenges. Well, first is the selection of an optimal threshold. And we conclude that a single threshold will basically, it's unlikely that it scales, will scale to a large network that has heterogeneous network traffic patterns. There will always be some cases that will trigger false alarms, and some attacks will be missed because there is just too much heterogeneity in the normal benign network behavior. And second, based on the results that we obtained, we saw that the methods have a large number of false alarms, false positives. So they cannot be deployed just as is to a real system, and some other techniques should be employed, secondary techniques, maybe some grouping of the devices into more homogeneous groups should be applied before using these anomaly detection techniques. And at the same time, we observed, we identified the IoT networks to have to be one of the most promising application areas, because IoT devices, as we saw, have more have a simpler network profile, and therefore they're easier to model, and the techniques produce more accurate results. So this is all that I have in my presentation. If you let me know if you have any questions, and if you would like to know more about this, please read my thesis report. Thank you.